Basic Calculus 5, Graph Sketching, Part 1 of 4. We're going to bring everything together. Let's start with a simple parabola. We know how to sketch this algebraically. We're going to use algebraic methods in the main, but we're going to use calculus to find the turning point. Just a bit of practice on a simple one. Y-intercept when x is 0, x-intercept when y is 0, quadratic equation, and we solve. Now, to use calculus methods, we're going to find the stationary point in this case, by putting the derivative equal to 0. So we differentiate and put equal to 0. Solve for x. Substitute back into the original to find the y value. And we have our stationary point. Now we need to find the nature of the stationary point. In this case, it's pretty obvious that it's going to be a local minimum, or absolute minimum, in fact, for the parabola. But let's go through the motions to get used to the calculus method. So we're going to find the second derivative. It's equal to 2. When we differentiate 2x minus 6, we get 2. That's always positive. So we say, well, that's positive. And that means it's always concave up, which gives us a local minimum. And there's the shape of the curve. Let's go on to a cubic. Y-intercept. X-intercepts. We equate that to 0. Now, there are a couple of ways of doing this. One is to use factor theorem to find the first factor, where we substitute the value of x to get 0. And then that gives us the first factor, and we divide to find the remainder and factorize. In this case, though, this is a simple case of grouping. If we group the first two, we have a common factor of x squared, and the next two we put in brackets. Notice the sign change. Now we have a common factor of x minus 1 comes out, and we have x squared minus 1 left, which factorizes further. And that gives us two x-intercepts. Those are equal roots there, equal zeros, which actually tells us that instead of having two separate ones, they've come together. So this actually, at this point here, it means we're going to end up with a turning point there. Derivative equals. Differentiate equal to 0. Now we're finding the coordinates of the stationary points by equating the derivative to 0. Factorize. So they're the x values of the stationary point. Now we need to find the y values by substituting back into the original. Use your calculator to do that. And if you could use your memory bank especially, that makes it very useful. And there's the first stationary point. And the other stationary point. Now we need to find their nature. We can see pretty much that's going to have to be a local maximum, and this must be a local minimum. But we must go through the working, particularly as later on you will hit some pretty complex functions where you don't know, you can't just recognize very easily whether it's a local minimum or maximum. So we find second derivative. We differentiate the derivative, 6x minus 2, and we say at negative 1/3, is that going to be positive or negative? Well, pretty obvious it's going to be negative, which gives us concave down, which is a local maximum. So there's our local maximum there. When we substitute 1 into there, we're going to get a positive, which will give us concave up, local minimum. There's our minimum. And we can pretty much see the shape of the graph now. Another example. Main difference being that now we have negative coefficient of x cubed. Y-intercept, when we substitute 0 for x, we get 0. X-intercept, we equate the equation to 0, multiply through by -1 to get rid of the negative on the x cubed. We're only allowed to do that because of the 0 here. Can't do it there, because if we did it there, we'd end up with -y. Factorize, and it gives us two x values. Once again, because that's x squared, that means there are two values, both 0, which tells us that two x-intercepts have come together as one, so that's got to be a stationary point. But that's just information useful to see. Derivative equals, so we differentiate. Minus 3x squared plus 6x. Equate to 0 to find the stationary points. Remember, at the stationary point, the gradient of the curve is 0. It's a horizontal line. Divide through by -3. I'm allowed to do it because it's equal to 0. Factorize, and there are x values of the stationary points. Now we must substitute those into the original to find the y values. So there's one stationary point and the other. Now we go to the second derivative to find the nature of those stationary points, whether they're concave up or down. There's our second derivative. I differentiated the derivative. Now say at x equals 0, is that positive or negative? It's positive. Positive means a local minimum. And there's the minimum shape. This one, x equals 2, -12, we're going to get a negative less than 0, which means a local maximum. There we have the shape of the curve, so we can slot it in now. Some examples for you to try. There are two screens of this. Try them first, and then answers follow. Y-intercept 0, x-intercept equal to 0, solve. Stationary points, derivative equal to 0, solve for x, substitute back in the original to get the y values, and there we have our stationary points. Go to second derivative. We're going to test the two x values of the stationary points. When we put 0 into there, we're going to get a positive. Oh, we put -2 in first. We're going to get a negative, so local maximum. When we put 0 in, we're going to get a positive local minimum. And there's our curve. Y-intercept, x-intercept, derivative equal to 0, substitute into the original. We now have our coordinates of our stationary points. Second derivative, differentiate the derivative. We're going to substitute 0 and 2 into this to see whether we get positive or negative. When x is 2, it's less than 0, maximum. When x is 0, it's greater than 0, minimum. Third one. Y-intercept 0, x-intercept equate to 0. That factorizes, it's actually a squared binomial. So we have two answers. Strictly speaking, we have three answers, but two of them are the same, which tells me it's going to be a stationary point at x equals 2. Differentiate, equal to 0, solve for x. Substitute in the original to get the y value. So we have 2/3, 32 over 27, and 2, 0. Now we're going to find the second derivative. We're going to substitute in 2/3, we're going to substitute in 2 each to find whether we get positive or negatives. Negative at 2/3, maximum. Positive at 2, minimum. There's our curve. Notice the local minimum on the x-axis, which gave us a hint because there were equal roots there, equal zeros. Second one. Get a lot of this sort of question, and they might seem confusing, but they're pretty straightforward. Use factor theorem to determine the factors of f of x. All right, so here we are, factor theorem. First step we have to do, well, we have to use trial and error. I try 1, -1, 2, -2 until I get 0 out of that. Well, 1 gives us 0. And if f of 1 gives us 0, we say, well, what sort of bracket would give an x value of 1 in an equation? Oh, x minus 1. So therefore, x minus 1 is a factor. Now, there are two methods to do this. I'm going to use division by inspection first, but I'll do long division as well. I've taken out a negative, so I'll have negative, and then in brackets 2x cubed plus 2x squared minus 10x plus 6 that I'm dealing with. There we are, like that. And I know that that's a 2 because x times what gives me 2x squared. Minus 1 times what gives me plus 6. There we are. So it's the m. So now when I multiply this out, there are two x squared terms. There's x times mx, and there's minus 1 times 2x squared to give me this 2x squared. That gives me m equal to 4, because we have m minus 2 equals 2. And we can now take the 4 and put it in place of the m. If this method worries you, we can do long division instead. We take x minus 1 and we divide it into the expression. Here it is there. Gives us 2x squared plus 4x minus 6, same answer. Notice I'm dividing into the inside of that. I'd rather take the negative out to fewer complications. Now that will factorize further. First of all, that has a common factor of 2. So I've taken it out and put it at the beginning, and that factorizes. Here it is. So we found the factors of f of x. Now we can find the intercepts of f of x with the x-axis, because if that's equal to 0, well, I've missed that, sorry. The intercepts are 1, 1, -3. Y-intercept -6. Differentiate, because we're now finding the x-coordinates of the turning point, equate to 0. I divide it through by -2. I'm allowed to do that because there's a 0 on the other side. Factorize, and they're the x-coordinates of the turning point. Substitute them into f of x. And that gives us the coordinates of the turning points C and D. Number 3. Function defined by f of x equals that. Calculate the intercepts with the axes. Well, y-intercept -5, x equal to 0. Equate that to 0 for the x-intercepts. And I'm going to use factor theorem first. I found that -1 substituted into there gives 0, so therefore x plus 1 is a factor. I know it has to be an x squared in order to give me an x cubed. It has to be a minus 5 in order for 1 times that to give me negative 5 there. I equate the x squareds. X times mx is mx squared. 1 times x is x squared. But it must be minus 3x squared. That gives us m equal to negative 4. Or we could have used long division. Either way, we end up with x squared minus 4x minus 5. Factorize further, and there are our x-intercepts. Discuss the, calculate the coordinates of the turning points of the graph of f. Derivative equal to 0, equal to 0. Divide through by 3. Factorize. And that gives us our x values of the stationary points. Substitute into the original to find the y values. So we now have the stationary points, the turning points of the graph. Discuss the values of f when x goes to negative infinity. Well, as we're going to the left, what's happening to the graph? It's going downwards, so which means it's going towards negative infinity. As we go to the right, the graph is going upwards, so it's going to, as x goes to infinity, y goes to positive infinity. Coordinates of points A, B, and C. Well, those are the axis intercepts. And local minimum and local maximum, we found the coordinates of those points and we can identify which is which just straight from the graph. Find dy by dx, so we differentiate. Show the graph has stationary points at 0 and negative 1 and find their coordinates. It's not a good idea to try to do it from there. You must actually go as if you didn't know those. Derivative equal to 0, negative 1, 0. There we are. We've done it. Find the coordinates. So we substitute to find the y values. And they're the coordinates of the stationary point. Determine whether each of these is a maximum or minimum or a point of inflection. And give reason for your answer. Well, if you show the working, that's your reason. Second derivative, differentiate the derivative, and we get a substitute negative 1 in and 0 in. Less than 0 at negative 1, we can see that hopefully, therefore a maximum. Greater than 0 at x equals 0, therefore a minimum. Sketch the graph of the function. Just need to get the x and y intercepts. And there's our graph.